What if I told you that the safety of our entire electrical grid really depends on, well, something as simple as dirt? Today, we're going to dig into the Wenner test. It's a fascinating method that helps us understand the ground right beneath our feet, and it all starts with a pretty basic question.
It sounds a little weird, right? But the answer is it can tell us a ton. The soil under us has these specific electrical properties that are, and I mean this, absolutely critical for designing safe and reliable electrical systems. We're talking especially about high voltage stuff, like substations. And the main thing we're looking for is something called soil resistivity.
So think of it like this. You know how a copper wire is a great conductor for electricity? Well, soil has its own built-in property to resist that flow of electricity. And that property, that's resistivity, is measured in ohm meters. Getting this number right is truly the first big step towards making sure everything is safe.
Okay, so why does this actually matter? I want you to imagine a lightning strike, or maybe a huge equipment failure at a power substation. All of that massive, dangerous energy has to go somewhere safe, and that somewhere is the ground. By measuring the ground's resistivity, engineers can design a system that makes sure all that energy spreads out safely, protecting people and the equipment.
So, to get this really important measurement, there are a few ways to do it. But the one you're going to see almost everywhere, the industry standard, is the Wenner test. Let's break down exactly how it works.
So, how do they do this out in the real world? Well, it's often called the four-rod test, and, that name gives you a pretty big clue about the setup.
The actual physical setup is surprisingly straightforward. An engineer literally just drives four metal rods into the earth, all in a perfectly straight line. Now, the key detail here is that they have to be spaced out equally. Then, you just run wires from each of those rods back to a special resistance meter. Okay, so here's what the little magic box does. The meter pushes a known amount of electrical current into the ground through the two outer rods. At the exact same time, it's measuring the voltage difference that pops up between the two inner rods. And from that current and voltage, it can calculate the resistance.
Now, here's the part you can't see. That electricity doesn't just travel on a straight line between the rods. Nope, it actually flows through the soil in this big, deep, bowl-shaped path. And understanding that path is totally key to knowing what we're actually measuring. Now, we've got to pause here for a second because this is super important. We have to distinguish between two terms, resistance and resistivity. The meter gives you a reading in ohms. That's resistance. But what we actually want is resistivity. That's an inherent property of the soil itself. Resistance changes depending on size and shape. Resistivity is the fundamental value we're after. So how do we get from that resistance number on the meter screen to the soil resistivity value that we actually need for our designs? Well, the answer is a pretty simple formula. This right here is the Wenner formula. And trust me, it's simpler than it looks. All it's saying is that resistivity, that's the Greek letter rho, is just 2 times pi times A times R. Let's break that down real quick. R is easy. That's the resistance value we just got from our meter in ohms. And A, that's that critical equal spacing we set up between our rods, and we measure that in meters. And here is the really cool part. That distance A isn't just a number for the formula. It also directly tells you the effective depth of your measurement. So if you want to know the resistivity 2 meters down, you just space your rods 2 meters apart. It's that simple. This lets engineers build a whole profile of the soil at different depths. The best way to really get this is to just walk through a quick, practical example. So let's pretend we're out in the field right now, taking a measurement.
First thing, we look at our meter. It's done its thing, and it's telling us the resistance is 7.4 ohms. All right, that's our R value. Easy enough.
Next, we look at our setup. We got out our tape measure, and we spaced our rods exactly 2 meters apart. So our A value is 2 meters, which also means we're measuring the soil's resistivity at a depth of about 2 meters.
All right, now we just plug those numbers into our formula. We've got 2 times pi times our 2-meter spacing times our 7.4 ohm resistance. You run that through a calculator and you get a soil resistivity of about 92 ohm meters at that specific depth. Done. But of course, the ground under a really big site, like a power substation, isn't going to be perfectly uniform. The soil can be totally different from one side to the other. So doing just one test is never ever enough. To really build an accurate model, engineers will do a whole series of tests all across the site. And you can see here in this sample data, they're taking readings at different spots.
A, B, C, and D, and at different depths. They even note the weather. Why? Well, because something as simple as a rainstorm can make the ground wetter and significantly lower the resistance, so having that context is totally vital. So now we've got a big table full of raw numbers. The next job is to turn all that data into something useful, some real insight. We need to find the patterns that are going to help us with the actual engineering design. So the very first thing you do is smooth out all those little local differences. For each depth you tested, you take all the readings from the different locations, A, B, C, and D, and you just calculate the average. This gives you a much better, more representative number for the whole site at that depth. And once you plot those averages, boom, a really clear pattern starts to emerge. You can see that near the surface, at 1 meter deep, the resistivity is up around 130 ohm meters. But as you go deeper, down to 2 or 3 meters, that value drops way down to under 100. So what's causing that drop? Well, this is a super common effect, and it's usually because of the water table. Deeper soil just tends to be wetter, more saturated with water. And wet soil is a much, much better conductor of electricity, which means it has a lower resistivity. This test has basically found the water table for us. So there you have it. From just 4 simple rods poked in the ground, we now have this detailed electrical map of the Earth under our site. This data is the absolute bedrock of safety. But the next big challenge is, how do you take these numbers and turn them into a real physical grid of buried copper that can actually handle a 1,000,000-volt lightning strike? Well, that's a great question for our next explainer.